All right, today we're going way back to basics. We're going to talk about the one element that's literally the backbone of, well, everything. From your breakfast to the t-shirt on your back, we are going to uncover the secrets behind carbon, the ultimate builder for life as we know it.
So let's jump right in. And we're going to start with a real head-scratcher, a mystery that's right at the heart of chemistry and biology. I call it the carbon paradox.
I mean, just think about it for a second. You are a carbon-based life form. The food you eat, the fuel in your car, it's all built on carbon. So you'd think it'd be everywhere, right? But, and this is the crazy part, when you actually look at how much of it is around, you find this massive contradiction.
And here's what I mean. Just look at these numbers. It's kind of wild. In the entire Earth's crust, carbon makes up a measly 0.02%. In the air we breathe, 0.03%. That's basically nothing. So how on earth does an element that's so incredibly rare end up becoming the absolute star of the show?
Okay, so the key to this whole puzzle isn't about how much carbon there is. Nope, it's about its personality, what it's like on an atomic level. It all comes down to how it plays with others, how it bonds.
All right, so here's the deal. Every carbon atom has 4 electrons in its outer shell. Now, to be stable, happy and content like the noble gases, it needs 8. So it has 2 options. It could try to grab 4 more electrons, but its nucleus, with only 6 protons, well, it just doesn't have the muscle to hold on to 10 electrons. Okay, option 2, it could just give away its 4 electrons. But that takes a huge amount of energy, so it's kind of stuck right in the middle. Neither option is a good one.
But instead of giving up, carbon finds this incredibly elegant workaround that honestly changes everything. It says, you know what? If I can't take them and I can't lose them, I'm just going to share them.
And this act of sharing creates something super important, a covalent bond. It's brilliant, really. By sharing electrons with other atoms, everybody wins. Each atom gets to feel like it has a full, stable outer shell. And this bond, it's not just some flimsy connection. It's incredibly strong, incredibly stable. This is the secret sauce to carbon's power. This is how it builds.
So this whole sharing thing, this covalent bonding, it leads to what you could honestly call 2 superpowers. These are the 2 special tricks that no other element can really pull off quite like carbon can. And it's what takes carbon from being just another element on the periodic table to being the ultimate builder.
And what are these superpowers? Well, they're called catenation and tetravalency. Now, catenation, that's just a fancy word for carbon's amazing ability to link up with itself over and over again to form long chains. And tetravalency, that just means 4 bonds. Because it has 4 electrons to share, it can form 4 super strong bonds at the same time.
Let's talk about catenation for a sec, because it's so cool. It's what lets carbon act like the ultimate Lego brick of the molecular world. Seriously. It can snap together to build long, straight chains. Think fats and plastics. It can create these complex, branched-out structures for really specialized molecules. And it can even form stable rings, which are the foundation for all sorts of important compounds. No other element has this kind of construction skill.
And the reason this works, the reason these structures don't just fall apart, is because that carbon-to-carbon bond is just so incredibly strong. Part of that is because carbon atoms are pretty small, so their nucleus can keep a really tight grip on those shared electrons. That stability is everything. It's why carbon can build the massive, complex molecules that life itself depends on.
Okay, so we've got these 2 amazing superpowers. What does carbon actually do with them? What does it build? Well, the short answer is pretty much everything that matters, from the hardest thing you can imagine to the soap you use to wash your hands. Let's just look at a couple of quick examples.
First up, let's see what happens when carbon just bonds with more carbon. Nothing else. These different pure carbon forms are called allotropes, and they are the perfect example of how just changing the way you connect the bonds can change, well, everything. Just look at diamond versus graphite. It's the same exact element, pure carbon, but in a diamond, every single carbon atom is locked into a rigid 3D grid with 4 of its neighbors. That structure is what makes it the hardest substance we know. Now look at graphite. Here, each carbon only bonds to 3 others, forming these flat hexagonal sheets that can just slide right past each other. That's why it's so soft and slippery. Same atoms, different blueprints, and you go from a priceless gem to the stuff in your pencil. Amazing. Okay, that's pure carbon. Now let's see how that chain-building superpower, catenation, is crucial for something you probably used this morning, soap.
The entire magic of how soap cleans you comes down to the structure of these carbon chains.
So a soap molecule is kind of two-faced. It's got two different personalities. On one end, you have this long tail made up of a chain of carbon and hydrogen atoms. This part is hydrophobic. It hates water, but it loves oil and grease. Then on the other end, you've got this ionic head, and it's the total opposite. It's hydrophilic. It absolutely loves water.
So when you mix soap and water, these molecules do something incredible. They automatically arrange themselves into these tiny little spheres called micelles. All of those oil-loving tails dive into the center to get away from the water, creating a little oily core. And all the water-loving heads stay on the outside, forming a shell that's perfectly happy to hang out in the water.
And this is how it gets you clean. Those hydrophobic tails see a speck of oily dirt, and they latch right on, burrowing into it. The soap molecules then swarm around the dirt, trapping it inside that oily core. Now you've got this little package, dirt on the inside, water-living heads on the outside. And that allows the whole thing to be just washed away with the water. It's like a perfect little microscopic cage for dirt.
So what's the big takeaway here? From just a couple of simple rules, a couple of superpowers, carbon has built an entire molecular universe. I mean, right now, chemists know of over 3 million different carbon compounds. And that's more than all the compounds of all the other elements put together. It's just mind-boggling.
Which really leaves us with one final big question to chew on. Carbon's incredible versatility obviously created the world as we know it. It paved the way for life here on Earth. But was that inevitable, a cosmic necessity? Or was it just a really lucky break for us? Could life somewhere out there in the universe have found a totally different way to build itself? Something to think about. Thanks so much for joining me for this explainer.